two weeks, right? We're at the 2 week mark, aren't we? Okay. Wow. Okay. So I think what I decided to do is not do chapter 5 at all. Skip chapter 5. Chapter 5 is cool, but I don't think it's 100% necessary, whereas perturbation theory is really important, for a lot of reasons. So I think we're going to go straight to chapter 6 for the last 2 weeks. Okay? We'll see how much of that we can get done. We might skip around. We might go chapter 6, chapter 7. Hold on a second. I'm going to grab the book. I don't have it sitting in front of me. Let's see. Look at the book. Yeah, we'll just see how it goes. I mean, once you know the time-independent perturbation theory, then chapter 7, chapter 8, chapter 9, and chapter 10 are very simple in some sense, because you'll have the idea if you ever need to go back, right? So if you're going to go to graduate school in physics, you will be learning all of that. So, okay. I guess let's start. Just get to the right place in the notes. Yeah.
About how long until we're going to get our test corrections back?
I don't know. I'll get to it soon.
Okay. Thank you.
Who turned in test corrections? You did, Jackson. Anyone else? Andrew, Jeff?
I did not.
Okay. Okay, well, then I'll get to yours quickly, okay, Jackson? I should be able to do it today sometime. And it's just turned in the same place. Is that right? Okay, good. All right, perfect. Let me share my screen. Okay. All right, so what we're going to study today is a very important technique for pretty much every single problem that you ever do. So you're aware that when you have the Schrodinger equation, right? So let's just look at the TISE. So we have the TISE, right? That's minus h bar squared over 2m partial squared, or actually, sorry, let me do this in 3 dimensions, although we're going to go back to 1 dimension, but let me do it in 3 dimensions. So
what's the title of the chapter?
It's time-independent perturbation theory. So this is, excuse me, we're about to sneeze. Time-independent perturbation theory. I can't spell, so I think it's perturbation. I have to go look it up. I'm a terrible speller. Okay. Time-independent perturbation theory. And the idea is this. So if we have the time-independent Schrodinger equation, so del squared psi is equal to, plus V of R. Now actually, and this could be even V of R theta phi, right? So there's no restriction on that. V of R theta phi psi is equal to E psi, right? This equation here assumes a couple of things, right? So remember that this equation is the equation that was separated from the actual Schrodinger equation, right? From the time-dependent Schrodinger equation, which is the IH bar. So then this was, okay, this thing here, the fact that this doesn't depend on time was the only way we could separate the TISE out of the TDSE, right? The time-dependent Schrodinger equation. So I'm kind of gonna, I'm trying to zoom kind of out to the big picture. So if we have the time-dependent Schrodinger equation, this is the fundamental equation of quantum mechanics, right? It's IH bar partial psi, and these are all supposed to be capital size. Oh, sorry. These are little size, but these are capital size. Partial t is equal to minus h bar squared over 2m del squared capital psi plus v of r theta phi t big psi. Okay, this is the fundamental equation in quantum mechanics, right? So, and this is assuming here that psi is, in general, a function of r, theta, phi, and t, right? Okay, now I've chosen spherical coordinates just because, you know, it's the most widely used 3D coordinates, right? Of course, I could have chosen Cartesian coordinates. In that case, this would just be v of, you know, you'd have your potential energy function as a function of x, y, z, and t. And your capital psi, the wave function, would be a function of x, y, z, and t, right? I just chose spherical coordinates just because it seems a little bit more general. Okay, now when we have this equation, I want you guys to think about a situation in real life, okay, not a problem like, say, the particle in a box, right? The infinite square well, or even the three-dimensional infinite square well, or the a hydrogen atom in isolation from every other hydrogen atom and every other atom and every other force, right? That's what we've been studying so far, are these systems that are these idealized systems that can teach us a lot. They're absolutely, right? But in the real world, things are a lot more messy. So very often you'll have some complicated function of some complicated, potential energy function. My pen's being really bad right now. Damn. This drives me insane. Hold on a second. I just want to see if I can get the activity monitor up and see what's taking all this processing power. Give me a second. Oh, man. Yeah, and everything's backed up right now. I'm sorry. Give me a second. Firefox. Let me kill Firefox. Yes, I want to kill everything. Yes, close tabs. Let's see if that slows everything down. Sorry, just hang on a minute. Let it shut everything down. Anyway, okay, so let's see if this is a little better. So this right here, this potential energy function, remember, this is what tells you what your system is, right? So this is what you specify because you're dealing with, say, I don't know, an atom in a lattice of other, silver atoms or something, right? Like there's lots of interactions that make this what it is, right? That make this potential energy function what it is. And remember, if you'd rather think about forces, which I don't know why anyone wants to think about forces, but if it's easier to think about that way, remember that del V is equal to the force, right? The forces, or the sum of the forces, right? Some of the net forces on the object. So if you want to think about forces, fine. Like there's all kinds of forces on, say, a silver atom in a net, in a lattice of silver atoms, um, and you might have some very complicated V, right? For which you can't separate, right? Because it's got a time dependence, and that is covered. So dealing with issues like that um, is like chapter 9. Okay, so we're not really going to deal with that
Is that epsilon a symbol or is it a sum sign? Or
here.
is,
That's a
yeah,
sum, right? Yeah,
okay.
right. Yeah. So net force, right? So I can write that also as F net. Okay. So you so if you have time dependence in it, right? You can't even separate, right, this equation into a TDSE and a time dependence that we've all known, right? So if you separate the time dependence, right, it looks like e to the minus I e t over h bar. Remember, right? So these are the separable solutions. This is under the condition that this has no time dependence. Okay, these solutions here are under that condition, right? If that is the case, then you get this, the time independent Schrodinger equation, and this is the time dependence. Okay, and these solutions here, and let me use a little different color here. So the solutions to this, and my Zoom is interfering for a minute. Give me a second. Okay, there we go. The solutions for this, so I should probably just unwrite that. All right. Psi, big psi of x and t, big psi, right, is little psi, and that's e to the minus I e t over h bar, right? And the little psi is the solution to this equation here. Right? These are the separable solutions. Okay. And those, so if this is the case, when you have no time dependence, then you can get these two equations. Okay, but I just want you to think about the most general case is when this could have, dependence on all three coordinates in space and time, right? And in that case, you can't separate, you can't use these two equations. Okay, you can't use the time independent Schrodinger equation. Okay. So what would you do? Does anyone have any idea if you had some really complicated V? Like, let's just make something up. E to the lambda t, I don't know,
Could you
p
try and segment?
theta, and, some sine phi, and 1 over r cubed. Just making this up. So let's say you have this. What did you say, Jackson? What would you do? You want to get psi, want this, right?
Could you try and like segment the time at like intervals?
Okay, it's a good idea. And in fact, what you would actually do, right, is use a computer to do exactly that, right? You would numerically solve this differential equation. It's not an easy task, even for a computer, and you have to use some pretty sophisticated code, which, it already exists. It's not like you have to make up code that does this. Most of the time, you don't have to make up your own code. Now, that's not always true. So even if you, well, okay, let's go back a little bit. So let's say even if you go to a Python library or, the numerical recipes book, and you find the algorithms to solve partial differential equations like this, and you stick this in, right, in here, and you have this big ugly differential equation. The when you've put all this into the computer, even if you've downloaded someone else's code, which exists, there's a lot of code that exists to do this kind of stuff. How do you know it's right? How do you know when it pumps out answers? Which it's going to pump out numerical answers, right? It's not like it's going to give you a function. It's not going to give you, psi of x and psi of r theta phi t is some, nice written down function like Legendre polynomials times, r to the L or something. It's not going to do that, right? It's going to give you numerical answers, right? So if you want psi at r equal 2, nanometers and theta equal 90 degrees, and et cetera, you'll get a numerical answer for that. Great. But how do you know it's right? Are you just going to trust it straight out of the computer? What do you think? Would that be a good idea or no? No, don't do that, please. Yeah, never, ever, 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 ever trust a solution when you come out of a computer, especially if something that's complicated. Yeah, when you put something into MATLAB and ask it what 2 plus 2 is, you're good because you already know the answer's 4. And if it doesn't give you 4, then you know something's wrong with your code, right? But you don't know the answer to this. You don't a priori know the answer, okay? You need some way of checking your code. And it would be great if the way to check your code also gave you some physical insight into the answer as well. Wouldn't that be awesome? Okay, so you have to have a way of checking it. You have to. You can never, ever trust the results of a computer without some check. And the thing we're going to study next, which is the time-independent version of perturbation theory, is one of the ways that you would check a solution. Now, in this case, I have also time dependent, so you'd have to use a different method than we're about to use. You'd have to use from chapter 9. Okay. Yeah, it's chapter 9, time-dependent perturbation theory. But still, right? You would have to use chapter 9. But if you have no time dependence, you can use what we're about to study. And the idea here is that, yes, what we'd like to do, so when you have a computer program and you've plugged in all your stuff and you think you've used it right and you've got your psi of, your psi numerical values for psi, you can make plots, right? What psi looks like for different r's and different thetas and different phi's, etc. Pick a time. You would like to see something on paper, right? You'd like to have something on paper to compare it to, right? Meaning, like, could you compare it for really small values of t? Or could you compare it at really high values of t, like when t goes to infinity? Does it have the right behavior? Can you compare it at really small values of r and really high values of r, right? Are there things that you know about what the answer should look like that can help you? Okay. So this is kind of along those lines. We use a way of estimating the wave function, right? To help us know what the true answer would be, and to give us some insight into what the physical consequences of the the strange V that you have here would be, right? Okay, so it depends on a couple of things. Well, let me back up a little. So say you have your numerical value that you have for big psi, your numerical function that you can make plots of and everything. The idea is that if you can write your V, right, your Hamiltonian, well, so the Hamiltonian is this whole thing here, right? Minus h bar squared over 2m times del squared plus b. That's the Hamiltonian, right? So Hamiltonian. So if we have a Hamiltonian here, minus h bar squared over 2m del squared, and let me let Haley back in, she dropped out, plus b, right? If you can write your Hamiltonian in terms of, making an approximation, say that this Hamiltonian is some known Hamiltonian, called it H0, plus some perturbation, all right, some extra piece, right? And maybe expanded in a series, right? Where you're acting these extra pieces, you're sort of expanding your really complicated Hamiltonian, which is this, in terms of a known Hamiltonian, plus perturbations where this is a small number. And the idea is then what you can do, right, if you can work this out on paper, then you can know if you can use this Hamiltonian to solve for size, you can have a psi associated with psi with the known Hamiltonian, plus lambda psi times the psi that you would get as the first correction, plus lambda squared times the psi you get the second correction, etc. So what you can do is you can crank through and find these psi 1, psi 2, psi 3, as many as you'd like to compare with your numerical solution, right? So there's a way of touching base with some other way of figuring out if you're right or not. Okay. Again, the biggest thing I want you to take away is that you never trust something when you write some code and you get some answer. You have to have some way of knowing if it's right. So never, ever, ever. That's one of the things that also I would highly encourage you to learn something like Mathematica, if you don't already know it, or Wolfram. You have good grasp of Wolfram Alpha, although it's not as powerful as Mathematica. Of course, they're built by the same people, obviously, but because when you do a bunch of algebra, this is also a thing that is kind of a pet peeve. When you do a bunch of algebra, and by a bunch of algebra, I mean like nothing like you've probably done so far, right, in any class, but like pages and pages of algebra that you might need for something, right? Calculations, that you should never trust that either. You need an independent check of that. And the independent check can be another human. Okay, fine. Get your friend to also do it without looking at yours. But a good thing to do is to check it all with a symbolic analyzer like Mathematica or Wolfram Alpha, right? That can also do algebra. Anyway, so you always need to have independent checks of things. Right? Always, always. Yeah. So I'll tell you a story. When I was a grad student, one of our papers, probably the last paper I wrote in astrophysics, was about these coupling constants between. So what that means is there's oscillations, and I don't know if you really ever thought about it this way, but if you have an oscillation that gets really big, if it has a really large amplitude, it can start coupling to other oscillations. Okay, so saying an oscillation is just by itself, say in a fluid, this is in neutron stars, is only it relies on the fact that your oscillations are small. But once the amplitude of an oscillation gets big, then it will induce oscillations in other modes in the star, let's say. And the coupling constants, if you've ever taken a look at any of my papers, I think I always assign people to at least look it over in one of the classes in one of the super classes, the IST 261. But it's 30 pages of extreme crazy algebra calculations, integrals, etc. And we were about to publish that paper, and we had all these numerical values for the coupling constants, which are really relevant to people that study gravitational waves, because we think that those oscillations in neutron stars could cause gravitational waves that are observable by LIGO. My friend Phil Aris, who's now a professor at UVA, we were writing the paper together, and he was checking all the calculations, right? And he found a 1 minus sign error. And this is something nobody had ever caught. Okay. It was my advisor, 2 other professors at Cornell, and myself and Phil. And he found 1 minus sign that made all the coupling constants at that level, because we're also using perturbation theory like this, right? Kind of like this, right? So all at the level of, say, lambda squared disappeared. So all our numerical values in our table were 0. And that was from 1 minus sign in like 30 pages of algebra. So it is super important. And what if we had been like, nah, of course it's right. I checked it. and 2 other people checked it. In that case, it was just horrifying. And it took 4 people to find that mistake. I mean, actually, Phil found it, but four of us checked it, and only 1 of us found it. Right? So it's really important. You have to know things are right, and it's really hard to do. And we did check some of that with Mathematica as well, but some of it we couldn't. There was just no way. It was too complicated to even put through Mathematica. Anyway, that's my speech for making sure that things are right. All right, so this is one of the techniques that's super important, like to think about, even if you never use perturbation theory and quantum mechanics, the idea of expanding things like a Taylor series, right, to try to figure out if you're doing something right is always useful. So this kind of idea is always useful, okay? All right, so let's narrow our focus now to one dimension, okay? We're just gonna deal with one dimension right now. And we're only gonna deal with potential energy functions that don't have time in them, okay? All right, so let's do a little example. We'll start with an example. Okay. So our example is we have, let's just think about the regular old one-dimensional infinite square well, right? And we're going to call that Hamiltonian H0. And remember that Hamiltonian is just minus h bar squared. So H0 is minus h bar squared over 2m d squared dx squared, because we're in one dimension, right? And the potential energy is 0, right, in the square well, and everywhere else it's infinity, right? We already know that. And the equation is that the TISE is the equation that we solved for the functions, psi, and we're going to label those 0 too. And we ended up with the 0th energies and the times the 0th wave functions again. Now, why am I saying putting 0 on everywhere? Because I'm going to use this as my known, right? We know the solutions to these, right? We know that psi n 0 is equal to the square root of 2 over a sine of n pi x over a, right? We know that. And we know the e zeros. The n zeros is n squared pi squared h bar squared over 2m a squared, right? We know those. Those are the known, right? But now what happens if we put in a little bump? So meaning here's the ISW, right? This is the normal ISW. Normal ISW. This is V. Right? So this is 0 and infinity everywhere, right? Everywhere else, right? But what if we put in a little bump? So here's the normal ISW. And then we put a bump in. Just a little bump. So instead of being 0 everywhere, there's a little bump somewhere that makes it non-zero, okay? Now, is the solution going to be this and this, do you think, for this system? What do you think?
It's under the assumption that that all of the energy, none of the energy is in potential energy, which isn't the case anymore with this.
Right, so it's not going to be that. Now, if the bump is little, right, then maybe it's going to be close to that. That's not an unreasonable assumption, right? And again, if you were solving a complicated problem that looked different from this, as long as you could say, hey, in some region when, not right now. Oh, I'm sorry, hold on. Man, I know, but you can't interrupt me right in the middle of class. Hurry up, hurry up, hurry up. Just close that up and leave it there.
Mhm.
Okay. All right. Sorry. So, you know, it's some. So if this system was anywhere near a system that you were trying to solve with a computer, right? In other words, let's say this bump is really big and you wouldn't expect it to be close to these, right? What you could do is vary parameters in your computer program so that you could solve it when the bump was small and then a little bigger, and you can add terms to make your solution closer and closer to what you expect, right? And that way check your computer program. So that's what this is all about. But we're just going to say, hey, we have a small bump. So the actual Hamiltonian, so this, right? This has, you know, some V that is not equal to 0. Oh my God, this is insane. I'm so sorry. Sometimes working from home is not great. Okay. All right. So this is V is not equal 0 inside, right? It's got a little bump. Okay. So there's a new Hamiltonian, right? So there's a new Hamiltonian, which is the full Hamiltonian. That's what we call it, right? The full Hamiltonian of this problem, which of course, when you act on psi, acts on the true psi, right? Which is not the psi n 0, and has a true energy, right? For the system. This is the notation we're going to use, which means like this is the, you know, the whole Hamiltonian, including the bump, right? Is a differential equation for the true wave function and the true energies. Okay. Now, what we're going to do, because it's a small bump, is we can say, hey, let's just let that small bump be h0, which of course is the one with no bump, plus some small number times a first perturbation here. And this is just an example, right? You can have many different perturbations, but this is the idea that this is the bump, and you have a small number here, lambda, which tells you it's a small bump, right? Okay. And then we're also going to write psi n, the true wave function, as an expansion around the wave function without the bump, right? Plus lambda, that same small number, psi n1, and I'm going to start putting parentheses around the superscripts, because it's going to, I don't want you to get confused that it might be like lambda squared, psi squared or something. Plus, second order lambda squared times some second order, so we call it second order correction, plus lambda cubed times some, third order correction. Think of a Taylor series, right? So the true the true psi n is an infinite sum, right? If you made this sum infinite, you would get exactly psi n, right? Right. So in other words, you go all the way up to lambda to the infinity, etc. So that's the assumption, and then the same thing with the energy. But the true energy is a correction to the 0th order energy in the same way. So we have E1 times lambda 1 plus lambda squared times E, the second order correction, plus ... Okay. And we call this, like I said, this is the first order correction. To the wave function, and this is the first order correction to the energy, and this is the second order correction here to the wave function, the second order correction to the energy, etc. So if you could take as many terms as you like, and there's a prescription for getting these corrections, and that's what we're after. Okay, so let's see if we can get an equation that tells us how to get these first order at least the first order corrections to both the energies and the wave functions. Okay. And let me point out something here before we move on. When you, in this example up here, we have some complicated V. You would also, of course, want to get E, right? E is one of the parameters that you're after. Right. So you would, your numerical solution would give you this and this. All right. Okay, so I need a new slide. So let me know when I can do that. Good. I'm gonna just get a new slide and label it while you're looking at this old slide. Okay. Sorry, I gotta rename this one here. Are we good? All right, so let's do it. Let's figure out how to get a handle on what these little corrections are, or at least what is the first order correction. So what I'm going to do is I'm going to execute H psi n equals E psi n with our expanded functions. So let's do that. So we're going to have, remember that H is H0 plus lambda H1, okay? And I'm gonna act that on my expanded psi n 0 plus lambda psi n first order correction plus lambda squared psi n times the, lambda squared times the second order correction plus, dot, 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 right? And then on the other side, I have the E's, E and 0 plus lambda E and the first order correction to the energy plus lambda squared E and 2. Okay. And then again times psi, right? So psi n 0 plus lambda psi n 1 plus lambda squared psi n second order correction plus dot, dot, dot. Okay, so now we're going to multiply through, okay? So we're going to try to collect powers of lambda. So let's look at powers of lambda to the 0.
So
Yeah.
why is it only with the Hermitian that you only have to go up to a certain?
Yeah, good question. So in this particular case, we are we're grouping all of the perturbation into one power of lambda in the Hamiltonian, and using the extra powers of lambda in the energy and psi. You could approach it, with more order perturbations in the Hamiltonian, but you're going to end up with roughly the same thing. Right? It's just going to be a different formulation. So this is kind of a standard that people do. Okay. All right. So let's look at powers of lambda to the 0. So let's just think about what we would get. So if lambda to the 0, right, we have this guy acting on this, right, on one side, right, and we have on this guy, if H0 acts on any of these other things, there will not be powers of lambda to the 0, right? It'll all be higher power. And if this guy here acts on anything here, it'll be not lambda to the 0 as well. So we have to go to look at the other side for any lambda to the 0 powers. So lambda to the 0 would be En H0, right? And then of course, if En acts on any of that, we're not going to see anything with lambda to the power 0, right? So for the lambda power 0, we're only going to get the two terms I have in yellow. So I'm just going to put them down here in yellow. We're going to have H0 psi n 0, and then we're going to have equals En0 psi n0, right? Now, why can I separate them into an equation like this? Does anyone know?
This would be the case for just the infinite square well, where the lowest possible psi is just 0,
Yeah,
right?
absolutely. Yeah, you're right about that. And also remember, lambda is is an independent thing here. So if we brought everything over to the other side, right, I would have h0 psi n0 minus en psi n0, and then I would have lambda times a bunch of stuff. Then I would have plus lambda squared times a bunch of stuff, all equals 0, right? So every one of those is in an independent equation, right? Right? Does that make sense? Because of lambda. Okay. Yes or no? Do I need to go through that? It's like when you have coefficients of, x and x squared and x to the fourth in an equation all equal to 0, right? Each one of those has to be 0 by itself. Right? Yeah, same thing here. Okay, let's look at the lambda to the 1 powers. Oh, sorry. That's not a parenthesis 1. That's an actual lambda to the 1. Lambda to the 1 powers. Let's look. Okay, how do we get lambda to the 1? Well, we're going to get this one here times this, and this times this, right? Yeah? Let me make that green a little bit more different from the yellow. Okay? And so this times this, and nothing else on this side. Okay. So, and then over here, we get this times this, and this times this, and nothing else. Am I right? So on this side, here we go, we have h0, right, times lambda. So I'm just going to leave the lambda out. Doesn't even need the lambda anymore. Psi n1, right, and then plus h1 psi n0. And those are the only two terms on that side. And on the other side, we have en0 psi n1 and plus en1 psi n0. Right? Yeah. And for lambda squared, terms that are lambda squared, let's look, right? We'll have this guy, again, on this, and we'll have this guy on this, right? And then over here, we'll have this guy on the squared term, just like over there. And we'll have this guy on this term, and one more term, which is this one, and it's getting a little messy in here, isn't it? On this, okay? So let's try to write all those down. So first we have h0 on psi, the second order correction of psi. And then we have plus the first order correction of the Hamiltonian times the first order correction of psi. Those are the only two terms on that side. And on the other side, we have En0, zeroth order energy with the second order correction of psi. And then we have the first order energy correction on the first correction of psi, first order correction on psi. Yeah, Jackson?
So the reason that you don't need to add the psi 1 and psi 2 thing Is that because both sides of the equation cancel each other out?
What do you mean you don't need to add the psi 1, psi 2?
Well, there would be, for example, like, uh, also there was one that you missed, the H2 times psi n to the 0.
You mean like here? This would be lambda squared?
Oh, wait, I forgot that we're only going to, all
Yeah.
right, never mind.
Yeah, and you're right.
Um,
There is a little bit of a, convention here that you only go to first order in lambda, but
okay,
I mean in H, yeah.
all right.
Um,
What I mean is, like, both sides of the equation are multiplied by psi squared, so they would just divide out and cancel each other out.
by lambda squared?
Yeah.
Yeah, lambda squared. Yeah,
Okay.
absolutely. Yeah. So again, it's kind of like when you collect all the, the coefficients of x and then the coefficients of x squared and the coefficients of, x cubed. If you have some polynomial that is equal to 0, right? Each of the coefficients of x squared, x cubed have to be 0 on their own for that to add up to 0. Right? Same idea here. Yeah.
And but there could be an e in. Okay, you were about to add that. Sorry.
Yeah. Sorry, there is one. En's the second order with the 0th order psi. Yeah, there you go. Right? And we're not going to deal with that second order equation probably. I don't think we do that. We ever do that? Maybe we do. Okay. All right. So now we have 3 equations. This one we already know about. This one's not exciting, right? We already know how to deal with that. This one, that's kind of interesting, right? It has the first order correction of the energy in it. It has the first order correction of psi in it. This one we probably won't deal with. We'll see. But let's look at the what's called first order theory. Okay. So first order theory really only deals with the first order corrections. So this is like, you really want a quick answer to what your computer should be spitting out. And if certain parameters you tune in your computer program, you tune them in a certain way that you can get a small perturbation, and then you can write down on paper what you think it should be and check your code, right? So first order means we're only going to deal with finding. So we're going to go first order theory is, what are E and 1 and, oh, for Christ's sake, I'm so sorry. That is not my kid's phone. Lord. Okay. We're going to go E and 1 and the first order corrections of the wave function. So what are these 2 things? Okay. So that's first order theory, and we're going to deal with this equation. Okay. And of course, we'll use this as well. Okay. All right. So let's look at this one equation. I'm going to write it down again in red or pink here. H0 psi n first order correction of psi plus the first order correction in H times the 0th wave function is equal to En, the 0th order energy, times the first order correction in the wave function plus the first order correction in the energy times the 0th order wave function. Okay, that's our first order theory, right? Okay. Now, what we're going to do is we're going to multiply both sides by psi 0 star. Okay, so by the 0th order wave function star. So I'm going to say we're going to multiply both sides. So by psi n 0 star. Okay, and integrate. And the notation for that is just our usual notation where we do this, right? We have psi n 0 inner product with the right-hand side of this equation. Sorry, right-hand side of this equation, our first order equation. So that's going to be h0 times the first order wave function plus h, the first order Hamiltonian times the 0th order wave function.
Wait, so which that's psi n0 to the x?
To the x? Is there an x somewhere?
Is that multiply both sides by?
No, this is star.
Okay, sorry.
By complex conjugate. Yeah. And that's the same as doing this, right? Remember, this is shorthand. Remember, so like, psi n0, psi m0 is shorthand for, psi n0 star psi m0 dx, right? Integral. That's shorthand, right? Okay. All right. So, and then on the other side, of course, we have psi n0 inner product with your E, your 0th order energy times the first order wave function correction, plus the first order energy correction times the 0th order wave function. And we can expand these. So I'm going to expand this side. So I have psi n0, and then I have h0 psi n1 plus psi n0 inner product with h, the first order correction of the Hamiltonian acting on the 0th order wave function. On the other side, expanding out, the e's, remember, are just numbers. So I'm going to pull those out of the integrals. And I have E n0, so the 0th order energy times the inner product of psi n0 with psi n1. And then plus the first order correction to the energy times the inner product of psi n0, psi n0. Now, I don't expect you guys to know what any of these things are, except for one of them. So of all the factors that are sitting on this page, or sitting on this slide, or whatever you want to call it, board, which one of them do you immediately know what it is?
Psi n0 to psi n0.
What's that?
That's just one, isn't it?
Yeah, exactly. So this is one. Okay, good. All right, so great. All right, that's excellent. So now if we look at the different terms and see what happens. Okay, so over here, this term here, remember H0. H0 is Hermitian, right? Which means I can take it from this side to the other side, yeah? And use it on the other side. Okay, so fine. And then I can deal with just this, but let's deal with term by term. So first thing I'm gonna do is I'm gonna take H0 to the other side. Okay, so H0, so this is going to be H0 acting on psi n0. Right? Okay. Okay. And I still have this term. Give me 1 second. Yeah, let me just write down this term. So I was writing everything down again. plus, now this one's just by itself. The first order correction in energy, right? Because this is 1. Okay, now look over here. So now this guy here is H0 acting on psi N0. What is that?
That's the same as En0 acting on psi N0.
Exactly. So this is En0 acting on psi N0. Okay, so I'm going to rewrite it one more time. So I'm going to pull the E out. Oops. Let me pull the E out. Here you go. En0 and then psi N0 psi N1 plus psi N0 H1 psi N0 is equal to En0. That's a 0. Psi N0 inner product psi N1 plus En1. Okay. Which one of these two terms cancel out? Which ones? There's 2 of them cancel.
The one we just pulled the E out of.
Yep, this one cancels with,
The one on the right-hand side.
yeah, this one. Okay, so what are we left with? We're left with psi N0 H1 psi N0. And people often write it like this, by the way, with an extra line here. But it's the same as what I just wrote. I'm going to turn it around. Okay. Tell me why this is an answer for getting the first order correction of the energy. Why is that true?
This would be the same as just normalizing it, right?
Kind of. Remember, you're acting. So this notation I find is often used when people are thinking of the matrix representation of a Hamiltonian. But it's still the same. Basically, what happens is you act the Hamiltonian on this psi, and then you multiply by psi N0 star and you integrate, right? So, but what do we know and not know in this equation?
We don't know what the total we don't know what the total energy of the system is, but we do know that all of the Hamiltonian is now in E.
Well, okay, so be careful. So this is the first order correction in energy, right? Because remember
Right.
that energy is this, the down up here, right? The 0th order plus lambda times the first order plus now, right? Yeah. So, but what do we know in this side of the equation?
We already know what theta 0 n is.
Yeah, psi N 0.
Psi 0. Sorry, not theta. Psi.
And we actually also usually know what H1 is, right? It's the perturbation that we're given. We're splitting up the Hamiltonian. It's not like this is a mystery and we don't know what H1 is, right? It's part of the problem, right? You're taking a Hamiltonian that is not like a Hamiltonian that you have a closed solution for, like the ISW, and you're saying, okay, I'm going to break it into the ISW Hamiltonian plus something, right? Some perturbation. That's H1. You know what H1 is in the problem. We haven't said what it is yet. We said it was a bump, but I'm going to do an example. I'm not going to actually use a bump. That's hard to to make it into a function. But right, so you usually know what H1 is. So here, you know what your base solution is that you're basing everything off, which is in this case is the ISW. You know it's psi n zeros, right? You know what H1 is. All you have to do is act H1 on psi n zero, right? And really, this is just an integral, right? So let's write down what the integral is. Really, this is an integral psi n zero star, and then H1 acting on, psi n zero dx. This is an integral. So you just have to do this integral, right? And all of these are known on this side. And then you get back the energy, the first correction to your energy. And again, when you're solving your differential equation, but using your computer, the energy is one of the things you get, right? Okay. All right, so let's look at, actually, let's just continue with this exact example, but with more concrete H1, etc. Yeah.
So the E in this instant, that's representing the total energy of the system, right?
Remember, it's collection. The total energy, if we come up here, it's a correction. So En, the actual total energy, is En0 plus, to be an expanded
Okay.
the corrections, right?
All right.
Right? And we're just getting the first order correction. It's like a Taylor series, right? You're saying, what is the, if I'm expanding around En0, what's my first order corrections when I'm close to En0?
Okay.
Right? Okay. All right. Can I go to another layer? Yeah, I hope. Okay. All right, so let's do an example. So again, we have H0 is for the ISW. Psi n0, as we've written down before. Oh, I don't use those, sorry. Psi n0 is the square root of 2 over a sine n pi x over a, and the En0 is n squared pi squared h bar squared over 2ma squared. Okay, all right, now let's let H1 be V0. So in other words, the unperturbed Hamiltonian, the unperturbed V is 0, right? And then when we perturb, we get this. Now, in this case, right, this is really, really not hard to solve, like completely analytically, meaning you can solve the TISE when V is equal to V0 super, super easily, okay? For instance, let's just look at it, okay? So I'm gonna look at the actual solution. So actual solution. Oh, TISE, sorry. TISE. Okay, for this. Okay, all right, what does that look like? It looks like minus h bar squared over 2m. So here we're actually going to solve the TISE for this situation. Okay, d squared psi dx squared plus v naught psi equal e psi, right? Well, I hope you agree with me that this can be transformed into minus h bar squared over 2m d squared psi dx squared, and then equals e minus v naught psi, right? Yeah. And that this looks exactly like the um, infinite square well with a changed e, right? Okay, with e prime. And therefore it's going to have exactly the same solutions, except for e is going to go to e, h bar squared, whoops, sorry. Right? So that's the equivalent. Okay, so this is not a hard thing to solve, but let's see what we get from perturbation theory. So perturbation theory tells us that if I want our first order correction to the energy, then we would get we would do this integral, psi n0 times the first order the correction of the Hamiltonian on psi n0, and to do that we take psi n0, and then when v0 is our correction acting on psi n0, and v0 is just a constant, so I can pull it out, so I get v0 psi n0 psi n0 with psi n0, and that is 1, as we know, and so we get the first order correction is v0 as we expect, right? So this is a trivial example, but it shows you that basically all you need to do is know this and know these, and you can get an answer for what the first order correction is. Yeah? Sorry that my kid, I don't know if you can hear him coughing, but he's like coughing lungs out, allergies. Anyway, so given a particular H, right, given a particular perturbation to the Hamiltonian, to get the first order correction, you just have to do a known integral, all right, with known things. Excuse me, man. Okay. Hold on a second. We're both getting allergy problems today. I think, well, yeah, so the next thing we need to do, right, is we've now figured out what the, how to get the first order corrections to the energy. But now we need the first order corrections to the wave function, right? We don't have those yet, right? We haven't found anything that's a first order correction of the wave function. So that's what we need to do next. Okay. All right. We can start with, if we let's go back to a different layer so we can take a look at those equations. Okay. If we look over here at this first equation here, you can see that there is a psi1 here and a psi1 here, right? So when you use that equation, I'm just going to rewrite that equation right here because we're going to use it on the other layer. So basically, we're going to collect all terms that are proportional to psi, the first order correction to psi, right? So we have H0 minus En0 times psi n1. And on the other side, I'll collect everything that's proportional to psi n0. And on the other side, I have I have E. What did I do that for? Hold on. I have minus H 1 and then minus E n1 psi n0, right? Okay, so that comes from that equation. So write that down, and I'm going to go back to the other layer. I'm only going to be able to
One
set
more
this up. Yeah, what was that?
Okay, thank you.
Yep. Okay. Okay, so let's write that again. So we're going to go looking for the first order, looking for the first order correction to psi. Okay. We're going to use that first order equation again, writing it down. H0 minus En0 times that first order correction we're after equals minus H1 minus En1 psi n0. Okay. All right. Now remember that these guys, the psi n0s, right, they form a complete set. That means any function in the space, in the Hilbert space, right, which all the sides here are in Hilbert space, meaning they're all square integrable, right? Any function in that Hilbert space can be written in terms of these, including psi n1. So in other words, I can say, hey, psi n1, because the psi n0 are complete, meaning they span Hilbert space, we can write psi n1 as a linear combination of psi m, and I'm going to write so in other words, we have some coefficients here, and we're summing over m, right? And we can write these functions, the first order corrections, as linear combinations of those of the complete set that we know, right? The sine n pi x's over a's, etc. Right? Those functions. Okay. Now there's a little subtlety here that I kind of hate to use, but we're gonna choose that m is not equal to n here. Okay, and the reason is so we're choosing. Oh, it's time. We're choosing m not equal to m basically to preserve normalization, but I'm going to get to that next time because it's 12:05. Okay, so sorry about that. We kind of come up right against the limit. You good? Can I stop the share now? It'll be on the video, obviously. All right, guys. Well, we'll see you on Thursday. Bye.